Imagine a function f that takes in a massive vector x from an n-dimensional space. Maybe n is 1,000, a million, or even a billion, like the weights of a modern neural network. We want to find the gradient, the vector of partial derivatives that tells us how the output responds to tiny nudges in every single one of those n directions simultaneously. Our physical intuition usually suggests that to know how n different things affect a result, we have to test them one by one. If evaluating the function once takes 1 second, then finding the gradient should surely take n seconds. For a million inputs, that is nearly 12 days of computation for just one gradient. But here is the central claim that drives the efficiency of modern computation. Let f be a differentiable function mapping Rn to R. The cost of computing the gradient of f is asymptotically no greater than the cost of computing f itself. When we say asymptotically, we mean that while computing the gradient might be slower than a single function evaluation by a constant factor, perhaps 3 or 4 times slower, that factor does not depend on n. Whether you have 10 inputs or 10 billion, the overhead remains a small, fixed multiple. This immediately tells us that our one-by-one intuition is fundamentally inefficient. Standard methods like finite differences, where you nudge each input slightly and rerun the code, are asymptotically suboptimal because they scale linearly with n. This section introduces a mathematical paradox. How can we extract n pieces of information for the price of just one? It feels like a magical trick, but as we will see, it is a direct consequence of how we structure the flow of derivatives. To understand why we need advanced techniques for differentiation, we must first establish a rigorous mathematical language and evaluate the standard numerical approaches. Consider a differentiable function, f, mapping an input space of dimension n in to an output space of dimension n out. At any point x, we define the differential, denoted as df, as a linear map that describes how small changes in the input translate to changes in the output. This map can be represented by the Jacobian matrix, which contains the partial derivatives of every output component with respect to every input component. Formally, the entry in the ith row and jth column of the Jacobian is the dot product of the ith basis vector with the differential applied to the jth basis vector. Essentially, the Jacobian acts as a bridge, mapping input perturbations to output perturbations. In the specific case where the output is a scalar, meaning n out equals 1, we define the gradient as the transpose of the Jacobian. This identifies the derivative as a vector in the input space. Now, the most common reflex for computing these derivatives is finite differences. The idea is simple. Perturb the input by a tiny amount alpha, measure the change in the function, and divide by alpha. However, this method faces a fundamental precision limit. In machine arithmetic, functions are only known up to a precision epsilon, which is roughly 10 to the power of -16 in double precision. If we use a very small alpha to reduce the mathematical approximation error, the rounding error, which scales as epsilon divided by alpha, explodes. Conversely, if alpha is too large, the approximation error itself becomes dominant. By balancing these two terms, we find that the optimal step size, alpha, is the square root of epsilon. This leads to a total error that is also on the order of the square root of epsilon. In practical terms, this means that even with 16 digits of precision in our function evaluation, we can only recover about 8 digits of precision for our derivatives. We lose half of our significant digits just by trying to compute a derivative numerically. To move beyond the limitations of finite differences, we look toward forward-mode automatic differentiation. This approach allows us to compute derivatives exactly, meaning they are accurate up to machine precision, by following the inherent flow of the program's code. At its most fundamental level, we can view any computer program that evaluates a function f as a sequence of elementary transformations. We represent this as f1 leading to f2 and so on until the final transformation fi. Each intermediate step maps a vector from one space to the next, starting from our input dimension n0 and ending at our output dimension ni plus 1. Mathematically, the function evaluation is the composition of these maps. To find the derivative, we apply the chain rule. The differential df acting on an initial perturbation delta x1 is the product of the differentials of each intermediate function, applied in the same order as the function evaluations themselves. We implement this by keeping track of the perturbation as it propagates. First, we compute the next state x2 and its associated perturbation delta x2 by applying the differential of f1 to delta x1. Then we use x2 to compute x3 and its perturbation, delta x3, and we iterate this process until we reach the final output. This propagation of perturbations is most elegantly handled using a data structure called dual numbers. Instead of simply storing a value x, we store a pair consisting of the value x and its perturbation, delta x. We then define arithmetic operations on these pairs. For instance, consider the product of two dual numbers. The value part is simply the product x times y. The perturbation part, however, follows the Leibniz rule for derivatives: x times delta y plus delta x times y. This allows the computer to calculate the function value and its derivative simultaneously in a single pass. However, there is a significant catch when it comes to gradients. If we have a function with a single scalar output but many inputs, we want the gradient. Forward mode AD computes the derivative in a specific direction defined by the initial perturbation, delta x1. To recover the full gradient, we must repeat this entire process for every basis vector of the input space. If our input space has 1,000,000 dimensions, we need 1,000,000 forward passes. This makes forward mode automatic differentiation efficient for functions with few inputs and many outputs, but computationally expensive for the high-dimensional gradients common in optimization and machine learning. To understand why computing gradients can be as efficient as computing the function itself, we must look at a simplistic but deep mathematical trick, taking the adjoint of the chain rule. In linear algebra, the adjoint of a linear operator is its transpose. If we have a linear map represented by a matrix A, its adjoint, A star, is simply A transpose. This concept is central to reverse-mode automatic differentiation. Recall that the differential of a composed function is the product of the differentials of its individual steps. When we take the adjoint of this entire composition, a fundamental property of linear algebra takes over. The adjoint of a product of operators is the product of their adjoints in reverse order. This is why equation 2 shows the adjoint of the total differential, df star, as the product beginning with the adjoint of the final step, dfi star, and ending with the adjoint of the first step, df1 star. This reversal of the operator sequence is the defining characteristic of reverse mode AD. Instead of starting with an input perturbation and pushing it forward, we start with a perturbation at the output, which we denote as delta x sub I plus 1, and pull it backward through the chain. The immense advantage of this formulation becomes clear when we consider the dimensions of our space. In forward mode, to compute a full gradient, we would need to track how every single one of the n input dimensions affects the output, requiring n separate passes. However, in the adjoint formulation, the number of required passes depends on the dimension of the output, n out. For most optimization problems or machine learning tasks, the function f is scalar valued, meaning n out equals 1. In this case, we only need a single perturbation at the output, specifically delta x sub I plus 1 equals 1, to represent the entire linear operator. By propagating this single value backward through the reversed chain of adjoint differentials, we obtain the full gradient vector in just one pass. This mathematical efficiency directly supports our initial claim. The cost of computing the gradient is asymptotically no greater than that of computing the function itself, regardless of how many input parameters n we have. We are essentially trading n forward passes for a single backward pass, a move that fundamentally changes the scalability of gradient-based optimization. To understand why reverse mode automatic differentiation is so powerful, we must look at the physical interpretation of the variables we are manipulating. In forward mode AD, we work with the perturbation, denoted as delta x. This answers a specific question. If I wiggle the input x1 by a small amount, how does that wiggle propagate through the function to change the intermediate value xi? It is a forward-looking causal relationship where the input change drives the output change. However, reverse mode introduces the reverse delta, often written as x bar or delta bar x. This variable represents sensitivity, not perturbation. It answers the inverse question. If I were to pause the computation at step I and nudge that intermediate value, how much would that nudge affect the final scalar output? This distinction is subtle but critical. In forward mode, the perturbation delta xi is caused by the input delta x1. In reverse mode, the sensitivity delta bar xi is caused by the final output's dependence on the result of step I. This is a complete reversal of causality. Usually, we think of step I determining step I plus 1. But in the adjoint world, knowing the sensitivity at step I plus 1 is what allows us to calculate the sensitivity at step I. This reversal has significant practical consequences for how we write software. Because the adjoint differential, df star, depends on the state of the system at that specific moment, we cannot calculate the sensitivities until we have already completed the entire forward pass. This means every intermediate value xi must be stored in memory. While forward mode is memory efficient because it only needs to keep track of the current step's perturbation, reverse mode requires a tape or a trace of the entire execution. This is the fundamental trade-off of automatic differentiation. We exchange memory for a massive gain in computational speed when dealing with many input parameters. It states that the inner product of the sensitivity, delta bar xi, and the perturbation, delta xi, is invariant across steps. Specifically, the inner product of delta bar xi and delta xi equals the inner product of delta bar xi plus 1 and delta xi plus 1. We derive this by applying the definition of the adjoint operator. If we take the inner product of the sensitivity at step I plus 1 with the perturbation at step I plus 1 and substitute the forward propagation rule where delta xi plus 1 equals the differential dfi acting on delta xi, we can move the operator to the other side of the inner product by taking its adjoint. This transforms the expression into the inner product of the adjoint differential, dFi star, acting on the sensitivity at I+1 paired with the perturbation at I. Since we define the sensitivity at step I as exactly that adjoint operation, the identity holds. This identity is the bridge between the two modes. Let's apply the adjoint theory to a fundamental problem in computational science, finding the gradient of a function that depends on the solution of a linear system. Imagine we have a linear equation LU equals F, where L is a matrix in Rn, F is our input vector, and U is the solution vector. We are interested in the gradient of a scalar-valued function f of f defined as the inner product of a fixed vector b and our solution u. This setup is ubiquitous. For instance, f could represent a physical measurement like the total heat in a system, where u is the temperature distribution controlled by the source f. To find the gradient, we first trace the forward flow of computation. We start with the input f, solve for u, and then compute f. Now, consider a small perturbation in our input, delta f. In our first computational step, we determine how this affects u. By differentiating the system, Lu equals f, we get L delta u equals delta f, which implies delta u equals L inverse delta f. In the second step, we propagate this change to the output. The change in f, denoted delta f, is the inner product of b and delta u. Substituting our previous result, we see that delta f equals the inner product of b and L inverse delta f. To find the gradient without the high cost of computing L inverse directly, we reverse the flow using the adjoint trick. We want to find a vector bar f such that the inner product of bar f and delta f equals delta f. In step 3, we identify the sensitivity of the output with respect to the intermediate variable u. From the equation for delta f, it is immediate that the adjoint variable, bar u, is simply the vector b. Finally, in step 4, we map this sensitivity back to the input f. We use the adjoint identity, which allows us to move the operator L inverse from the right side of the inner product to the left side as its transpose. This reveals that the inner product of b and L inverse delta f is equal to the inner product of the transpose of L inverse times b and delta f. Since the inverse and transpose operations commute, we conclude that the gradient delta f is equal to the inverse of L transpose applied to b. The critical insight here is that we never actually compute an inverse matrix. Instead, we obtain the gradient by solving the adjoint system, LT bar f equals b. This solve has exactly the same computational complexity as the original forward solve, meaning we can calculate sensitivities for high-dimensional inputs with remarkable efficiency. While the linear case is straightforward, the adjoint trick truly shines when we tackle nonlinear problems where dependencies are defined implicitly through constraints. Consider the objective function f of a equals x transpose bx, where x is a normalized eigenvector of a symmetric matrix A corresponding to a simple eigenvalue lambda. Here, x is not just a simple function of a. It is defined by the system ax equals lambda x and the constraint that its norm is 1. To find the gradient of f with respect to the matrix A, we must first understand how x changes when A is perturbed. This brings us to our first computational step, differentiating the constraint equations. If we perturb A by delta A, then x and lambda must also change by delta x and delta lambda to maintain the equality. Differentiating ax minus lambda x equals 0 yields delta a times x plus a times delta x minus delta lambda times x minus lambda times delta x equals 0. By grouping the terms involving the perturbations of our variables, we arrive at the expression. The quantity A minus lambda times the identity multiplied by delta x minus x times delta lambda equals negative delta A times x. In our second step, we differentiate the normalization constraint. The norm of x squared equals 1. This gives us 2x transpose delta x equals 0, which geometrically means any change in the eigenvector must be orthogonal to the eigenvector itself to maintain unit length. Third, we combine these into a single block matrix system. We define a Jacobian matrix J that maps the changes in our variables to the changes in our constraints. This Jacobian has a specific block structure. The top left block is A minus lambda I, the top right is the column vector negative x, and the bottom row is 2x transpose followed by 0. This allows us to write the relationship as J times the vector of perturbations, delta x and delta lambda, equals the vector negative delta ax and 0. Step 4 involves solving for delta x. Because lambda is an eigenvalue, the matrix A minus lambda I is singular, having a rank of n minus 1. This is where the Moore-Penrose pseudo-inverse, denoted as A minus lambda plus, becomes essential. It allows us to invert the relationship within the subspace orthogonal to the singular direction, leading to the result delta x equals negative A minus lambda plus times delta A times x. Finally, in step 5, we compute the forward differential of our goal function, f. Since b is symmetric, the variation delta f is simply 2x transpose b delta x. By substituting our previous expression for delta x, we find that delta f equals negative 2 x transpose b times the pseudo-inverse of A minus lambda times delta AX. This completes the forward pass, mapping the perturbation delta A all the way to the change in our objective delta F. Having established the forward differential for our eigenvalue problem, we now perform the reverse pass to find the sensitivity of the objective function f with respect to the matrix A. This involves reversing the sequence of dependencies we derived earlier, going from the variation in the final value, delta f, back to the variation in the eigenvalue, delta x, and finally to the variation in the matrix, delta A. This process relies on the adjoint identity, where we map sensitivities through the transpose of the Jacobian. In our first computational step, we map the sensitivity of the objective, hat delta f, back to the eigenvalue sensitivity, hat delta x. From our forward pass, we know that delta f equals 2 times the transpose of bx times delta x. To find the adjoint, we use the inner product relationship between delta x and its adjoint variable. By substituting our expression for delta f, we find that the sensitivity of the eigenvalue, hat delta x, is equal to hat delta f times 2 times b transpose times x. This provides us with our first intermediate value, the vector representing how changes in the eigenvalue impact the final objective. In the second step, we propagate this sensitivity further back to the matrix A. We recall the forward relation where delta x equals negative the pseudo-inverse of A minus lambda applied to delta A times x. We set up the adjoint relationship by taking the inner product of delta x and hat delta x. Substituting our expression for delta x, we obtain the inner product of negative the pseudo-inverse of A minus lambda times delta A times x and hat delta x. This expression describes how the matrix variation, delta A, influences the eigenvalue sensitivity. Step 3 requires us to extract the matrix delta A from this inner product. We utilize the trace identity, which defines the inner product of two symmetric matrices as the trace of their product. By rearranging the terms within the trace using the property that the trace of a product is invariant under cyclic permutations, we can rewrite our expression. Specifically, the inner product becomes the trace of negative x times the transpose of the quantity pseudo-inverse of A minus lambda times hat delta x, all multiplied by delta A. This algebraic move is the key to isolating the matrix-level gradient. Finally, in step 4, we deduce the explicit formula for the gradient hat delta A. Since the matrix A belongs to the set of symmetric matrices, the gradient must also be symmetric. We combine the terms from the trace to find that hat delta A equals negative x times the transpose of the pseudo-inverse of A minus lambda times hat delta x minus the pseudo-inverse of A minus lambda times hat delta x times x transpose. This final result is remarkably efficient. Once the forward pass is complete and the pseudo-inverse is known, we can compute the gradient of the entire matrix using simple vector outer products. This demonstrates the power of the adjoint trick in handling complex, constrained nonlinear problems. Is backpropagation just a fancy name for the adjoint trick in a specific context? In the world of deep learning, the answer is a resounding yes. When we look at a neural network, we are essentially looking at a composite function, where each layer is a discrete step in a long chain of computations. Specifically, a simple neural network is defined by a sequence of functions, where each layer I takes an input xi and produces an output x plus 1 through the transformation fi of xi equals f of wi times xi plus bi. Here, wi is our matrix of weights, bi is a vector of biases, and f is a nonlinear activation function. The adjoint trick applies directly here to compute the gradient of a scalar loss function f with respect to every single weight and bias in the system. The process is split into two distinct phases. First, the forward pass involves evaluating the network from the first layer to the last. During this phase, every neuron I must remember its value. This requirement for storage is exactly why deep learning requires significant amounts of memory. We cannot compute the gradients later without knowing exactly what values were present during the initial evaluation. Let us look at 3 explicit computational steps to see the adjoint logic in action. Suppose we are at layer I. Step 1 is the forward computation of the pre-activation vector, zi. We take the input xi, multiply it by the weight matrix wi, and add the bias bi to get zi equals wi times xi plus bi. Step 2 completes the forward step for this layer by applying the nonlinear activation function. The output xi plus 1 is calculated as f of zi. This value is then passed to the next layer and simultaneously stored in memory for the backward pass. Finally, step 3 is the backward pass, or the adjoint step. To find the gradient of the loss with respect to the weights wi, we start with the sensitivity of the loss with respect to the output, which we call delta xi plus 1. Using the chain rule, we first find the sensitivity of the pre-activation, delta zi, by multiplying delta xi plus 1 by the derivative of the activation function, f prime of zi. Then we find the gradient for the weights as delta wi equals delta zi times the transpose of the stored input xi. This result, delta wi, equals the element-wise product of delta xi plus 1 and f prime of zi, multiplied by xi transpose. This allows us to update our parameters to minimize the loss. This backward pass is simply the adjoint equation being solved layer by layer, moving from the loss function back toward the input. We now transition from discrete neural networks to continuous time, which is the domain of ODE solving and the foundation of neural ODEs and sensitivity analysis in physics. Imagine we want to compute the gradient of a final result ft of x0, which is some scalar function b of the state x at time t. The state itself evolves according to a differential equation, x dot of t equals f of t and x of t. To differentiate this through time, we first consider the forward differential. If we perturb the initial condition x0 by a small amount delta x0, how does the final result change? This is step 1. We establish that the change in the objective, delta f, is the gradient of b at the final state dotted with the perturbation of the final state, delta x of t. Step 2 requires us to find how that perturbation evolves. By linearizing the dynamics, we find that the time derivative of delta x is the Jacobian of x with respect to x evaluated along the trajectory multiplied by delta x of t. This is a linear ODE. In step 3, we define the adjoint state, which we will denote as delta tilde x of t. We want this adjoint state to track the sensitivity of our objective with respect to the state at any time t. Crucially, we observe that at the final time t, the sensitivity is simply the gradient of our objective function, b. In step 4, we use a clever trick. We require the inner product of our adjoint state and our perturbation to be constant for all time. This ensures that the sensitivity we calculate at the end is the same as the sensitivity at the beginning. If we differentiate this inner product with respect to time and set it to 0, we apply the product rule to get the inner product of delta tilde dot and delta x plus the inner product of delta tilde and delta x dot. Finally, in step 5, we substitute our expression for delta x dot and use the definition of the adjoint operator to move the Jacobian. This reveals the adjoint ODE. The time derivative of delta tilde x is negative the adjoint of the Jacobian times delta tilde x. This is a new differential equation that we solve backwards in time, starting from our known terminal condition at time t and integrating back to time 0. This backward flow allows us to recover the gradient with respect to the initial conditions in a single pass, mirroring the efficiency of backpropagation in a continuous regime.